Okay, so we have spent the first 2 weeks of this semester talking about the structure of atoms, actually the history of atoms. Why do we believe things are made of atoms? And what does the atom look like? Protons and neutrons in the nucleus, and then the electrons are somehow surrounding the nucleus, and we've come up with an entire wave mechanical model to describe the exact positions of where electrons are in atoms. They're in regions of space called orbitals. And over the last couple days, for the homework for sure, you had to use something called the periodic table because you had to look up numbers on the periodic table. So what is this? We're going to spend this week talking about the periodic table, and that's going to conclude by the end of Wednesday all the material you're going to need to know for test 1. Okay? Now, the periodic table was not developed in order for you to determine molar masses of elements, determine electron configurations of elements. The periodic table was a method to try to organize elements in groups that have similar properties. And the history is sort of a sad one, so you might need your crying towel with you, so be ready. Here we go. The first person to actually think about the chemical elements in terms of grouping them with similar properties was the German chemist Johann Dobereiner. And Dobereiner recognized that there were several groups of elements that came in groups of 3 that had similar properties. He called these groups of 3 triads. And so Dobereiner's famous triads were chlorine, bromine, and iodine. These were all very reactive, volatile, colorful elements. Calcium, strontium, and barium were very reactive metallic elements that were very similar in properties. Sulfur, selenium, and tellurium were non-metallic type of elements that were chemically very similar to each other. Lithium, sodium, and potassium were all very soft, silvery metals that were very explosive with water, very reactive. So Dobereiner was the first one to recognize that the chemical elements that Robert Boyle had defined for us as things that could not be decomposed into simpler substances, and they knew about maybe 60 substances that could not be decomposed. So at this time, we knew about 60 elemental types of matter. He was starting to recognize that those elements could be grouped together based upon their properties. And so he's the first one to discover families of elements. So these triads were the precursor to what we call families of elements, the word family denoting similarity, so that the groups of elements that had similar properties. Now, maybe 30, 35 years after that, an Englishman, John Newlands, came up with something a little bit more inventive. He noticed that if you took all the known chemical elements and put them in order of lowest atomic mass to highest atomic mass, something really interesting happened. It appeared that the chemical properties of the elements repeated every 8 elements. So Newlands noticed that if all the chemical elements were arranged by increasing atomic mass, the properties repeated every 8 elements. And Newlands came up with a table of the elements, putting them in order of lowest atomic mass to highest atomic mass. And his table looked something like this. The first element they knew of lowest atomic mass was hydrogen. He wrote it down. The next element was lithium. He put it 1 over. So we have hydrogen and lithium. The next, and the reason they had lithium is that helium hadn't been discovered yet. Helium wasn't discovered till the end of the 1800s. So the first 2 elements that were known were hydrogen and lithium. Beryllium had different properties than hydrogen or lithium, so we put it in its own column. Boron had unique properties. Carbon had unique properties. Nitrogen had unique properties, and oxygen had unique properties. Then when he got to the element fluorine, fluorine had similarities to hydrogen. So instead of making an 8th column, he put fluorine underneath hydrogen. So columns are going to denote elements with similar properties. And then here's what he noticed. Oh my goodness. The next element we know, which was not neon because it wasn't discovered yet, was sodium. And sodium is an explosive reactive metal just like lithium, identical. Magnesium is chemically the same as beryllium. Aluminum and boron are similar. Silicon and carbon are similar. Nitrogen and phosphorus are similar. Oxygen and sulfur are similar. And then when you got to the next element, chlorine, that's just like fluorine and hydrogen. Boom, he put it under there. And he thought that he had come up with a characteristic pattern of the properties of elements. He called this the Law of Octaves. Why did he call it the law of octaves? Because do, re, mi, fa, sol, la, ti, do. If you go a major harmonic scale, not a chromatic scale for the music majors, of course, but a harmonic scale, then the musical note repeats every 8. And the chemical elements were doing that as well. And Newlands was very taken by this, and he felt that he had really come up with some cosmic kind of property of the chemical elements related to music. And he actually attended a giant symposium on the continent of Europe, and with all of the other chemists and physicists in attendance, he presented his law of octaves to them. And they started to look a little bit more closely at the elements past chlorine. And when they did, they went, wait a second, look at this. Titanium is nothing like boron and aluminum chemically. And what? Manganese, the same as oxygen and sulfur? That's not true. And so they said, no, Newlands, that is completely bogus. And you know how we have cancel culture today? Well, this was cancel culture in the 1800s. And they essentially booed Newlands off the stage. Newlands was very fragile. He did not take that very well, went back to England, committed suicide. So that was actually really a sad event in the history of the periodic table. But Newlands actually was onto something. If we start arranging the elements in order of increasing atomic mass, maybe there's some pattern to the elements repeating their properties. And then just a few years later, a Russian chemist, Dimitri Mendeleev, he was actually teaching students at the University of St. Petersburg. And if you're a chemist, you have to go there someday. So I went there back in 1991, and this is the University of St. Petersburg. And there's a little picture of Dimitri Mendeleev right on the side of the university right there, right by the front door. So what he was doing is he was trying to teach his students about the properties of the chemical elements. And to make it a little bit more easily understandable, he did what Newlands did. He arranged them by increasing atomic mass. And when he did this, he wound up leaving spaces if an element didn't belong in a particular column. And this is something that Newlands did not do, but this was really significant. So he arranged the properties of chemical elements by increasing atomic mass. He put them in columns if they had similar properties, but he left a space if an element didn't belong in a particular column. So let's take a look at Mendeleev's attempt at arranging the elements in a periodic table. So he had in his periodic table, and you can look at this on Wikipedia, they actually have it from the original paper. You've got 8 different columns on there. Now the properties he used was what formula would a particular element make when it formed a compound with oxygen. So if it took 2 atoms of an element to bond with 1 oxygen, that was column 1. If it took 1 atom of the element to bond with an oxygen, that would be column 2. If they bonded in a 2-to-3 ratio, that'd be column 3, a 1-to-2 ratio, column 4, etc. So if we take the first known element, hydrogen, how does hydrogen bond with oxygen? It makes the compound H2O. Pink, it goes right there. And once again, the next element they knew wasn't helium. That wasn't discovered yet, but they knew lithium. And Mendeleev said, well, what kind of compound does lithium form with oxygen? Li2O. It's the same as what hydrogen does. So I'm not going to put it in the next column like Newlands did. It's got to go in that first column. So he stuck lithium here. And then when he used the next elements in order of atomic mass, beryllium formed BeO, goes in column 2. Boron, B2O3, goes in column 3. Carbon, CO2, goes in column 4. Nitrogen, N2O3, goes in column 5. Did something different for oxygen because oxygen doesn't make a compound with oxygen, but it would go in the next column based upon other data. Fluorine would be F2O7. And so the next 6 elements fit exactly like this. And then when he got to the next element that was known, which was not neon, it was sodium. Sodium forms a compound with oxygen whose formula is Na2O. So he put it underneath hydrogen and lithium. And the rest of the elements in that row just fit right into the pattern as well. So when he went to the 4th row, when he went past chlorine, then he got to the point where he had element potassium, which was just like sodium. Element calcium was just like magnesium. It formed MgO and CaO. But when he got to titanium, and this was the key, titanium did not form a compound with oxygen. It was Ti2O3. It formed TiO2. So he was trying to group the elements by their properties. So he said, I'm not going to put it in that 3rd column. It goes in the 4th column. and vanadium goes in the 5th, chromium goes in the 6th, manganese goes in the 7th. He had some other elements that all went into the 8th column, and he continued his periodic table. Anywhere an element not fitting into a particular column's property, he left a blank there. But the elements were arranged in order of increasing atomic mass. So what he was able to do is he was able to state what we now call the periodic law. And the periodic law, according to Mendeleev, was the properties of the chemical elements are not arbitrary, but they vary in a systematic way if you put them in order of their atomic mass. They don't have to repeat every 8. There is no law of octaves, but we do know that, watch this word, periodically, every once in a while, the properties start over again. And that's why it's called the periodic law. So the properties of the chemical elements are not arbitrary, but vary with their atomic masses in a systematic way. And maybe it was true, maybe it wasn't. But what was significant about what Mendeleev said is that he looked at his periodic table and he looked at these holes on here and he said, you know what? I think we have some elements that have not been discovered yet. And Mendeleev was able to predict the properties of elements that weren't discovered. And in fact, a very famous one was right here. How come there's no element there underneath titanium in that column right there? Well, what he did, and there were actually more columns in the periodic table. There was a column 6 and 7. So there were some elements above and below this spot. So he took the densities of the elements above and below it, took their average and said, this element is going to have a density that's equal to the average of the elements above and below it. He took the atomic masses of the elements above and below it. And he said, when we find this element, whatever it is, I predict its atomic mass is going to be 72. And he made all these predictions about this particular element, which he called the element beyond silicon, ecosilicon. And then, 25 years later, the element ecosilicon, which we now call germanium, was discovered. And the properties that Mendeleev had predicted back in 1869 was almost exactly what the properties of ecosilicon were when it was discovered in 1886. And the chemists went, oh my gosh, I think Mendeleev is right. So the fact that he was able to predict the properties of undiscovered elements led people to believe that the properties of the chemical elements are not arbitrary, but they vary systematically. And it's important to understand, we're in the 1800s here, right? Nobody knew that protons and electrons existed yet. They thought atoms were indivisible objects. So they had no idea that the internal structure of the atoms might cause them to have specific properties. So they were just going on experimental data. And there was no reason for anyone to believe that atoms or elements would repeat their properties in some systematic way. But the fact that Mendeleev was able to predict the properties of undiscovered elements, they went, oh my gosh, it's got to be true. Now, why do the properties repeat themselves in a systematic way? They had no idea, but it was quite obvious that they did, okay? Now, unfortunately, as time progressed throughout the 1800s, people became more accurate in their chemical laboratory skills, and they were more accurately able to determine atomic masses. And when they were calculating atomic masses more accurately, errors appeared in Mendeleev's table. And if you look at the periodic table and you arrange all the elements in order of atomic masses, the properties repeat themselves in a systematic way usually. But you know what? Right here they don't. Look at those two atomic masses, 58.9, 58.6. Mendeleev would have had to put nickel first and cobalt second, and now the elements don't have similar properties in their columns. Look at this, 127, then 126. You need to switch those elements. Iodine needs to go first, tellurium needs to go second. When you do that, the columns are now not all similar properties. So there's some little thing wrong. Mendeleev spent the rest of his life trying to figure out what was wrong with the periodic table, but unfortunately he died before an answer ever surfaced. He never knew why there were these small errors in his periodic table. Because the answer didn't come till 1912, when an English physicist named Henry Mosley was working on measuring frequencies of X-rays from excited atoms, nothing to do with the periodic table whatsoever. So he measured the frequencies of X-rays being emitted from excited atoms. Now, this is similar to what we did in lab in experiment 3. You zapped atoms with electricity, and you caused them their electrons to jump to excited states, and the electrons dropped back down to their ground states, and they emitted forms of electromagnetic radiation. They were giving off visible light, ultraviolet light, infrared light. Those aren't photons given off of very high energy. How do you give off X-rays? That's when you excite the nuclei of atoms. So we cause the nuclei to be excited. The nucleus can go to an excited state, but there's so much more energy involved in the nucleus. When it drops back down to the ground state, it gives off photons of much higher energy. So those are X-rays and gamma rays. And so he was measuring these. And so what he did is he took all the chemical elements he tested, and he recorded on the x-axis their atomic masses, because that's what they knew then. So I just picked a sample of the elements. I'm starting with tin, which had an atomic mass of 119, antimony's at 122, iodine's 127, tellurium's 128, xenon's 131. And he wound up, when he looked at his graph, he goes, "God, I got like some atoms that are close to each other, like iodine and tellurium are really close, but antimony and iodine are really far apart from each other." And he didn't like that spacing not being even. So he decided to make up a new property of each of the atoms, and he called it their atomic number. And so he assigned each element a number. He started hydrogen 1 and worked his way up from there. So when he did that, when he got to tin, tin was 50, antimony was 51, iodine was 52, tellurium was 53, xenon was 54. And then when he looked at his graph, he said, "Oh my goodness, look at this. Almost all of the elements, I have graphed their X-ray frequencies versus my made up atomic number. They almost lie perfectly in line, except for a couple. Iodine and tellurium seem to be messed up there. Maybe what I should do is I should take iodine and tellurium and switch their spots." So when he switched their spots, bink, oh my gosh, they went right on the line. So he said, "Wow, that's really interesting. This atomic number must be something more significant." And he thought about the periodic table, and he said, "Oh my gosh, what if Mendeleev would have put his periodic table in order of my newly invented atomic numbers instead? Then all the elements would be in their proper columns, and then the periodic law would absolutely be true. Properties of the chemical elements repeat themselves in a periodic, systematic way." So Mosley in 1912 found that the X-ray frequencies of excited atoms were proportional to the atomic number of the atoms, not the atomic mass. And then when you apply atomic masses to Mendeleev's periodic table and atomic numbers instead of atomic masses, then all of a sudden, all the columns worked out perfectly. So the periodic table was changed. Instead of writing the elements from lowest atomic mass to highest atomic mass, they wrote the periodic table in terms of its elements from lowest atomic number to highest atomic number, whatever this was. He wasn't quite sure at the time that atomic number meant the number of protons. We later found that out. But his work changed the periodic law. And so what I gave you before is technically not correct. This is the periodic law as we understand it now. The property of the chemical elements vary in a systematic way. They repeat periodically with atomic number, not atomic mass. And that's where we are today with the periodic table. It's a way to categorize elements into similar properties if they fit in a column, and all we do is we arrange them from lowest to highest atomic number. If you write an atomic number, and as soon as you get to an element that has a similar property of other ones, you move it over and you put it underneath that element. And so our periodic table that we look at today has the first row as only 2 elements. There's hydrogen and helium, because they're very much like the elements in the very extremes. And then the next row of elements, you have to go 8 elements across before the properties repeat themselves. The next row, you go 8 elements before the properties repeat themselves. Then you have to go 18 elements before the properties repeat themselves. Then 18 before the properties repeat themselves. Then 32, then 32. So Mosley, when he was working with the X-ray frequencies, he was 23 years old. He graduated early with his PhD in physics, really sharp guy. That was 1912. What happened in the world in the next couple of years after that?
World War I.
World War I.
So Mosley was drafted, and Mosley went across the English Channel, was fighting in the trench warfare in France and was killed. And after World War I, the British Parliament said, oh my gosh, we had a 23-year-old scientist that was brilliant that we sent to battle and we killed him. So they passed a law that they would never ever draft one of their scientists again because of the death of Mosley. But his one contribution at the age of 23 was that he was able to figure out what the periodic table should have been organized as. Now, some terminology concerning the periodic table. If you talk about a row on the periodic table, so a row is horizontal, just so you know, that's called either a period or a series. And on the periodic table, they're numbered. The highest row, the first row, is called the first period or the first series. This is the second period or second series, third period or third series. And so the yellow one shown here is called the fourth period or the fourth series. So keep going down, there's 5, 6, and 7. So we go down to the seventh period or seventh series. If you talk about a column on the periodic table, these are called a group or family. The name family, once again, connoting that these elements have similar properties, much like you and your siblings are kind of similar to each other. The groups or families are numbered 1, 2. They don't number these, but then they number them 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And this goes 13, 14, 15, 16, 17, 18. So the main elements you find in a normal periodic table that are not broken out, if you take those out, the columns are labeled 1 to 18. Some old periodic tables, they 1, 2, and they skip all the way over to here, and they go 3, 4, 5, 6, 7, 8. But the more modern periodic tables, they're actually, oh, let's see, I gotta fix my computer. It's dying out a little bit here. Let's see what's wrong. Oh, yes, yes, yes. Plug it in. Okay, there. So those are how we essentially number the columns on the periodic table, okay? Now, we've seen that the periodic table can tell us information about the electron arrangement of atoms, specifically their valence electrons. And so this is something you need to know, and we've already had it on past homework assignments. If you're in the first column on the periodic table, you have 1 valence electron. If you're in the second column, you have 2 valence electrons. If you're in the F or D section, you have 2 valence electrons, except for the chromium and copper columns. And then the last 6 columns go 3, 4, 5, 6, 7, 8. So why do columns have similar properties? They didn't know at the time, but you now know with 20/20 hindsight, the elements in columns have similar properties because they have similar numbers of valence electrons. That's really what determines the property of elements to a major extent. It's how many valence electrons they have. So elements in columns have similar properties because they have the same number of valence electrons, if that makes sense. Okay? Now, once you arrange the elements in the periodic table, arranging them by atomic numbers and then repeating if they have similar properties, then there are some trends that appear, and we're going to learn 3 specific properties of the chemical elements that come from the periodic table itself. So these are called periodic trends. Give me a second, I'm going to stop. I just want to make sure things are working out okay. Let's see. Oh, I see. One more adjustment. Ah, way better. Unprepared, how unfortunate. Okay. Where were we? I think here. Can you see that? It says periodic trends of atoms?
Yes.
Yeah.
Good, perfect. So we're going to be able to predict 3 properties of atoms based upon the atom's position on the periodic table itself, okay? And these properties, come on, work. That looks like it froze. There we go. They involve the attraction of either an outer shell electron or a free electron to the nucleus of the atom. And this concept we're going to need to understand because all of the periodic trends we're going to learn are all based upon this phenomenon here. So the trends on the periodic table can all be predicted by describing how an outer shell electron or a free electron that's flying by an atom can be attracted to the nucleus of the atom, because it depends upon two things. And here we go, let's take a look at an atom. So in an atom, the nucleus is colored in red, and then the outer shell electron means any of the electron or electrons in the highest occupied energy level. So what's going to cause an attraction between the electron at the very top, which I have as the only electron in the third energy level of this atom, and the nucleus? What determines how strongly those attract? So you have to think about that. There's two properties that influence the attraction here. The first is the nucleus. It depends upon how many protons are in the nucleus. How would that affect the attraction between the nucleus and the outer shell electron? More protons be more attraction, or less protons be more attraction?
More protons.
Exactly.
Mean a greater attraction.
So that's going to be an important concept for you to know. So if you're trying to explain a periodic trend and I ask you why does X, Y, or Z happen, it's going to be because of the number of protons, and that means the more protons, the more the attraction will be. The second factor is going to be the number of energy levels that are blocking or shielding the nucleus from the outer shell or from the free electrons. That's a second factor. So the attraction of the outer electron to the nucleus, that line in green I have there between the outer electron and the nucleus, is affected by the charge of the nucleus itself, and then the number of shielding energy levels. Look at my picture. How many shielding energy levels are there in this particular atom?
3.
There's actually 3 total energy levels. The shielding energy levels are the ones that are blocking. So if we're trying to see what the attraction is for this electron way out here, for this nucleus, this one's blocking and this one's blocking. So I would say there are 2 shielding energy levels, if that makes sense. Is quickly that good?
Oh yeah, sorry.
Perfect, okay? So here we go. We're gonna talk about at least one trend today. We'll see how far we can get and see if we can explain this to you. And then over the course of tomorrow, we'll hit the other 2. So here we go. The first thing you can predict about atoms, just based upon their position on the periodic table, is their atomic radius, which means how big they are. Now, atomic radius is the radius of a sphere. It's just the distance from the nucleus to the outer shell of an atom. So if you have a spherical atom and the nucleus is in the very center, the distance from the nucleus to the outer shell electron or electrons constitutes its radius. So the bigger the atomic radius, the bigger the atom is, if that makes sense, okay? So I'm going to talk to you about the natural trend on the periodic table for atomic radii. You'll need to know the trend. You may have learned it in a previous class, but what I'm going to expect you to know this semester is why. So here we go. So periodic trends and atomic radii. We're going to talk about the trend of the atom sizes in a period, which is a horizontal row, and in a column, we'll do them separately, then we'll combine them together. So the first thing I want to do is talk about what happens to the size of the atoms as you move from left to right across any row on the periodic table. And as you go from left to right, let's say we have lithium at the very left and goes beryllium, then boron, then carbon, then nitrogen, then oxygen, then fluorine, then neon. What happens to the radii of the atoms? What happens to their sizes? Well, it turns out that the atomic radii decrease as you move to the right across any row on the periodic table. So if you have lithium at the very left side of the second row on the periodic table and neon on the very right side, neon's small, lithium's big. The atoms get smaller moving to the right. Why is that? Because this is what I will ask you on your exam. Why? So let's take a look at a couple of atoms that are in the third row on the periodic table. And I know they're in the third row because this atom has 3 energy levels, okay? Atoms in the first row put all their electrons in the first energy level. Atoms in the second row put all their electrons in the first and second energy levels. If you're in the third row, you need to use the first, second, and third energy levels to hold all your electrons. If you're in the fourth row, you need to use the first, second, third, and fourth energy levels to hold all your electrons. So that's an important thing about rows on the periodic table. They're telling you how many occupied energy levels a particular atom has. So this is an atom in the third period of the periodic table. This might be sodium because it has 11 electrons in it. There's going to be some attraction between the nucleus and the outer shell electron. Let's go one element over, and one element over from sodium is magnesium. Now, what's the difference? A sodium atom has 11 protons in its nucleus. A magnesium atom has 12 protons in its nucleus, so the nuclear charge will be bigger, and I'm going to signify that by drawing a bigger nucleus. Can you see that? Ooh, bigger charge in the center, okay? This is now magnesium because there's an extra electron. Here's the extra outer shell electron in the atom, okay? So how is magnesium different from sodium in the two factors we talked about, nuclear charge and shielding energy levels? How is magnesium's nuclear charge compared to sodium's?
Would it be greater?
Because it now has 12 protons instead of 11, it's bigger. So that means this attraction here must be stronger because the nuclear attraction is greater. If the attraction is stronger, what's it going to do to the outer shell electrons? Pull them in. Okay, so that's what you need to understand. If you have stronger attraction, you're going to pull the electrons closer to you. So the fact that there's more protons in the nucleus is going to actually make a magnesium atom smaller than a sodium atom. Now, what's the other factor? Shielding energy levels. So how many shielding energy levels are there in my top atom, sodium? How many shielding energy levels are there in my sodium atom?
3.
No, try again.
Sorry, 2.
Perfect. The outer shell doesn't count, right? Because the attraction's between the nucleus and the outer shell. So there's the first and second energy levels that are shielding. How much shielding is there in the magnesium atom?
2.
It's the same. Did this added electron, is that a shielding electron?
No.
No.
No, that didn't go in the first or second energy levels. It's kind of irrelevant. So when you analyze the two things that influence the attraction between an outer electron and the nucleus, the nuclear charge and the number of shielding energy levels, well, the outer shell electrons in magnesium are attracted by an increasing nuclear charge while the shielding of the nuclear charge remains the same. You didn't change any shielding whatsoever. So the atoms get smaller, moving to the right across the periodic table because as you move to the right, you're always increasing the nuclear charge. The atomic number is getting bigger. Now you're also increasing the number of electrons, but the electrons are going into the outer shell. They're not going into any shielding shells. So as you move to the right, the nuclear charge increases while the amount of shielding stays the same. Therefore, the atoms will get smaller. If I ask you to explain any periodic trend, I have to hear in your answer what's happening to the nuclear charge and what's happening to the shielding. If you only say magnesium is smaller because it has a greater nuclear charge, half off, because you didn't tell me what's happening to the shielding. You have to say, oh, wow, the shielding remains the same. Do we have any Led Zeppelin fans out there? There's always at least one in every class. Led Zeppelin?
I mean, I'll listen to it.
Okay, what was that? What was that documentary that they made about Led Zeppelin? Did you ever see that? Famous documentary? It always reminds me when we talk about this, while the shielding of the nuclear charge remains the same, that documentary, the shielding remains the same. Did you ever see that?
No, I did not. I gotta look into it.
Okay, yeah, sounds too bad. Actually, the name wasn't The Shielding Remains the Same, it's The Song Remains the Same, but that wouldn't have worked out very well with my joke. But I always think about Led Zeppelin anytime I think about this. Shielding remains the same, okay? So don't forget that when you're answering your question, why do the atoms get smaller as you move from left to right across the periodic table, okay? So that's the trend in a row. Let's talk about a column. In a column or a group on the periodic table, the atomic radii will increase moving down a column. And that may be a phenomenon you may have learned in a previous chemistry class, but now I'm going to want you to tell me why the atoms get bigger as you go down a column. So let's take a look at two different atoms in a particular column. I'm going to go to the first column on the periodic table. I'm going to show you an atom that has 3 electrons, so it therefore has 3 protons. So this is an atom of what element if it has 3 protons and 3 electrons?
Lithium.
Lithium.
Yeah, that's a lithium atom, okay? So lithium atom has a certain size, whatever it is, because there's some attraction between the nucleus and the outer shell electron. The nuclear charge is +3, and how many shielding energy levels are there?
1.
Muy bien, okay? Let's go down the column to sodium. As you go down a column, what always happens to the atoms? You have to add another energy level. So that's the difference. If you look at sodium now, it has 1, 2, 3 energy levels. Now notice what's the same. Lithium has 1 valence electron. Sodium has 1 valence electron, right? Elements in a column have the same number of valence electrons. But now there's a couple of differences between these 2 atoms. What's attracting in the lithium atom is a +3 nucleus, and it's being blocked by 1 shielding energy level. What's happening down here? The nuclear charge is now +11. That's a lot bigger, but there are 2 shielding energy levels. So I'm going to ask you 2 questions. Don't jump ahead and try to get to the final answer. Don't miss these questions. Okay, first, because sodium has a greater nuclear charge, what should that do to the attraction to its outer electron compared to lithium's? Just because it has a greater nuclear charge, that should make the attraction for the electron greater or smaller?
Greater.
Should make it greater.
Should make it greater, which means it should pull the electrons in, and sodium should be a smaller atom, right? Now, what's true about the number of shielding energy levels of sodium compared to lithium?
There's more
Sodium
shielding.
has more shielding.
Greater.
More shielding. Would you think more shielding would make the attraction between the nucleus and the outer electron greater or less?
Less.
Less.
Because you're blocking it more. So we have 2 things that are diametrically opposing each other. Sodium has more protons, which tries to pull the electrons in, but it has more shielding, which blocks the attraction, so the electron doesn't get pulled in. So in all reality, if logically you're trying to predict if a sodium atom is going to be bigger or smaller, no way to do it. You have to know which one of these 2 effects is more prominent. And it turns out the more prominent effect is the number of shielding energy levels. If you can increase the number of shielding energy levels, you block that nuclear charge so much that the atoms get bigger. So even though the nuclear charge is increasing, and whoever has their microphone on, if you can turn it off, even though the nuclear charge is increasing, the outer shell electrons are more shielded from the nuclear charge, and so the atom winds up getting bigger.
So, Professor,
Yep.
in a sense, because there's more electrons in the energy levels, those electrons are diluting the force that the protons are adding.
Yeah, exactly right.
Okay.
Like you go to the beach and there's a campfire and 6 people stand in front of you instead of 1. That's going to make you a whole lot colder. Exactly correct.
Okay.
Yeah. So listen to my answer. Can you hear me addressing both phenomenon, nuclear charge and shielding? Because you have to be able to do that. Even though the nuclear charge is increasing, which means you would pull the electrons in more, even though that's happening, the outer shell electrons are more shielded from the nuclear charge. That overcompensates for the greater nuclear charge, so the atoms are bigger. This is why the atoms get bigger going down a column. Is the end of all question?
Yes. What exactly by is the nuclear charge? What does that
That's how
mean
many
exactly?
protons are in the nucleus. Each proton has a charge of +1. So a lithium atom would have 3 protons in its nucleus. Its charge would be +3. Sodium has 11 protons in its nucleus. Its charge would be +11. So that's a greater nuclear charge. That should attract negative electrons more strongly.
Yeah. Okay.
But if you have more shielding, that overcompensates for that. And so therefore the outer electron cannot attract the nucleus as strongly. And so the atoms get bigger. Make sense? So if you were looking at the periodic table, could you predict to me what atom has the largest atomic radius?
It's cesium, right?
It's the one farthest.
Bottom left.
Yeah, bottom left, and actually on the periodic table, francium is at the bottom.
Francium.
So that would be the biggest. Francium has the biggest atoms of all the elements on the periodic table. Okay? Which is the atom that has the smallest, what element has atoms of the smallest atomic radius?
Helium.
Top right.
Have to be the top right. Hydrogen and helium only have one energy level each, but as you move to the right, helium has more protons in its nucleus, pulling the electrons in more closely, so the helium atoms are the smallest. Does that follow?
Yeah.
So on the periodic table, largest atoms here, smallest atoms here.
Shervin, I think you're echoing because you're unmuted.
That makes sense? So that's your first periodic trend. It's a diagonal periodic trend, smallest atoms in the upper right, biggest atoms in the bottom left. It's a combination of this trend of what happens in columns, what happens in rows that I will expect you to be able to explain to me on our next homework assignment and eventually on the test. Now, each of these periodic trends we're going to talk about, there will be some exceptions. And there's one exception to this in terms of predicting sizes of atoms on the periodic table. And this exception happens to appear in the D block of the periodic table. And it's an exception that happens as you go down a column or down a group. So if you're in the D block of the periodic table and you go down a column, the atoms do not necessarily get bigger and bigger going down the column. And I want to see if we can explain to you why this exception occurs. So we find that atoms that are in the 5D sublevel section of the periodic table are not larger than atoms in the 4D sublevel section. Atoms in the 5D sublevel section of the periodic table are not larger than atoms in the 4D sublevel section. When you look at the D block on the periodic table, the highest row in the D block are the 3Ds. Then you go down to the 4Ds, then you go down to the 5Ds. So what I want to do is I want to look at the atomic radii of atoms in a particular column in the D sublevel section. I'm going to look at a 3D atom, then a 4D atom, then a 5D atom. I'm going to show you their radii and see if we can figure out why the radii are what they are. Now I'm going to do the fifth column on the periodic table, which is the column that has vanadium at the top. Its atomic number is 23. And we've done experimental measurements of the size of vanadium atoms. We know they have a radius of 0.122 nanometers, okay? The element directly below vanadium that's now in the 4D row on the periodic table is niobium. And niobium has an atomic number of 41. And niobium, we would expect to be a bigger atom because it has one more energy level, so it has more shielding. And even though the nuclear charge is increased from 23 to 41, the extra level of shielding cancels that out, and the atoms can't be attracting the nuclei can't attract the outer electrons as strongly, and so the atoms are bigger. And we go down to tantalum, which is right below that, atomic number 73, we would imagine the same thing. There are more protons, but more shielding energy levels will cancel that effect out, and the atom will get bigger. What we find is the niobium atom actually is bigger, okay? And if I were to ask you, why is it bigger? We would say, well, you actually have more protons in the nucleus. There's 18 more protons. That's trying to make the atom smaller. And you have one more energy level block in the nuclear charge. That's trying to make it bigger. So when you're in a column on the periodic table, there's an increasing factor and a decreasing factor. What's trying to make the atom bigger is one more shielding energy level. But there's something trying to make it smaller, right? And that's more protons in the nucleus. So for niobium, the increasing factor is you have one more shielding energy level, but the decreasing factor is you have 18 more protons, and the one more energy level wins out. And so therefore that causes the atom to be larger. That's why it's 0.134 instead of 0.122. When you get down to tantalum, the radius is 0.134 again. It's exactly the same. Now, what's the increasing factor? It has one more shielding energy level, What's the decreasing factor? What's trying to make tantalum a smaller atom?
The amount of protons.
And how many more protons are there?
32.
Oh, there are, and that's significant. There's so many more protons that those extra protons suck in the atom and they exactly cancel out the one more energy level. So when you get to the 5D block on the periodic table, for some reason, the number of protons in the nucleus is going to be 32 more protons than the atom right above it. And that's so many protons that actually cancels out the fact that you have one more energy level trying to block the nuclear charge. Look in the periodic table. Here are the elements. When you go from vanadium to niobium, you only have to add 18 more protons because it's only 18 more elements over till you get to niobium. But to get to tantalum, you have to go 32 more elements over. Why is that? Because look at this. What's that? The F sublevel fills before you get to tantalum. The first row in the F sublevel is the element lanthanum. So sometimes the 4F section of the periodic table are called the lanthanides. So we'll see when we go from the 3D to the 4D to the 5D section in the periodic table, the 5D elements are almost always the exact same size as the elements above them, because to get to the 5D block, you have to pass through the entire 4F block first, which means you're putting 14 extra protons in the nucleus, and that's called the lanthanide contraction. So the lanthanides cause the 5D sublevel metals or elements to contract in size, so they wind up not being bigger, but equal in size to the 4D elements.